Okay, hi, hello, welcome in everyone. I know it's a little cramped, this room. Technically, I think is only supposed to be 25 people, like in terms of on the room book, but that's truly all that was available. So we're rolling with it. We're out here. Welcome to section at a weird classroom, weird time, right before holiday, long day. Here's the QR attendance code. If you can, go ahead and scan it, fill it out. Today's like random question is just like, what's your favorite breakfast food? What's your go-to? Are you like a sausage, egg, and cheese croissant? Are you cereal? Are you what are you? For those of you who submitted what's the song of the summer, I will be sending out a song of the summer playlist, Spotify playlist. It is quite eclectic. We are all over the place, but it's fun. Um, so sorry about the crazy long announcement. That was scary. If it makes you feel any better, it took me like an hour or more to write, and then I like showed it to like two people. And I was like, "Is this too much?" It's mostly just we want you to succeed, and also the exam is kind of the first point in this entire course where you get legitimate feedback on your work. And I don't want that to be like a scary time, and I don't want people to be like unprepared for that. And so that is where it comes from. So game plan for today is we're going to be doing a bunch of stereochem stuff from lecture. I've kind of divided it up into, I don't know, maybe one, two, three, four, five, like six chunks. And I've tried to make it very skills focused because lecture four, this 3D stereochemistry stuff, a lot of it is like the skill of drawing chairs, the skill of doing EZ, the skill of doing RNS, the skill of deciding what's the relationship between two molecules. So hopefully we can get work done on those skills to help you with the problem set and for practice exams and everything. Um, are there any kind of logistic questions or things on people's minds that either about the exam or practice exams or like game plan for the next week? Slay. The other thing is the vibe been getting from people is people are still very stressed about lecture three, which is so valid. Like if you think that like after 2 days from lecture three, you should be like, got it. No, she's gonna take a while, and like she's gonna be like working every day up until the exam to get there. It is the hardest one by far. I don't think anyone's got it right now. So like you are in good company with that. Also like again, if I was in your shoes, I would feel very stressed after lecture three. So like that is normal. And so keep on with the practice. Hopefully the section videos materials is helpful. There's also the Klein OCHEM as a second language book, and in the detailed course logistics from like the first section and on Canvas, it has a concordance table that tells you like which chapters in which book to look at for each of the lectures. So if you were like, actually, I can't even start lecture three. Lecture three is crazy. I would say go and look back at that because that honestly is the book that taught me organic chemistry. Like it taught me carbonyl chemistry that y'all learned yesterday. But without further ado, let's start jumping into things. So first up, we are going to start out with this labeling system and these priority systems, just because I think that they are kind of the easier skills. Like they are a kind of concrete thing that you can practice and get good at. And they're very like algorithmic in their approach. So, in the past, you've probably seen cis and trans alkenes, and now we've introduced this newer system that's a little bit more powerful in terms of naming alkenes. It lets us name alkenes with more than just two substituents on them. So, what we do is we divide a double bond down the middle, and then we look at the top and bottom parts on our alkene, and then we have a little game that we play, and we rank the higher priority of the two parts. If the highest priority is on both the bottom or both the top, we say that the alkene orientation is Z. It's on Z-same side. And then if they are on opposite sides, we say it's E or epicit, which I actually think is really fun and cute, but Logan apparently did not appreciate. So let's go over the rules, our kind of like order of like who wins. They're called the Kohn-Ingold-Prelog rules. You don't need to know that, but like if you ever see that, that's what it's referring to. So the first thing that we look at is atomic number. So the highest atomic number wins. Second thing that we look at is isotope. If you have two elements, it's the same element, but you have different isotopes, the heavier isotope wins. And then the third thing that we do is we list out the substituents on that atom. And so whichever has the highest atomic number substituents wins. And then if these are ties, we just keep going out and out. You saw some in lecture. Let's try to do some again. So we're going to do this first one together. So we are dividing down the middle of our double bond, and let's look at the left side over here, comparing top versus bottom. So first off, atomic number, we have a tie, right? And then this 18 here is indicating that this is oxygen 18 versus the normal one, oxygen 16. So this is an isotope of oxygen. So we have isotopes, the heavier isotope wins, and so we would say our bottom one wins down here. And one thing that I like to do, like I know different people have different amounts of writing they like to do for these. One thing I think is very helpful is to star top or bottom, whichever side wins. Because then, and when you're in the last step of deciding E or Z, it's helpful to like make it really clear for yourself. Okay, then on the right side, we're comparing top versus bottom. We have a carbon for both, so it's tied. We look at substituents. So what are the substituents on this top carbon here? We have some hydrogens and carbons. So we have carbon, and then we have two hydrogens on here. Carbon, hydrogen, hydrogen. And the bottom, do we have the same thing or a different thing? Same thing, carbon, hydrogen, hydrogen. Okay, we go out one further. We have carbon versus carbon. Same deal here. Substituents on the top, we have the carbon going down, we have the bromine, and we also have the H. On the bottom, we have carbon, chlorine, and the H. And so we're tied with the carbons, tied with the hydrogens. Which has the highest atomic number between bromine and chlorine? Bromine. There we go. So the top one wins over here. So if we have one top, one bottom, are we the same side or are we on the opposite side? Opposite. So this is E, or entgegen, if you're fancy. Cool. So I have 3, and these are ones that I just like fully made, and I tried to do it with the tricks and normal traps in mind. So take a few minutes. I think I'm going to give you about 3 minutes to try these out, ranking them, doing the whole priority rules, and then we will come together and check them, okay? And yeah, sorry that space is tight. Feel free to like move it wherever you want. Ooh, great question. So D is called deuterium, and deuterium is an isotope of hydrogen, H2. I think Logan mentioned it in lecture today, but normally hydrogen just has a proton. It has a mass of 1. So this version, technically its fancy name is protium, like proton, and this is deuterium, like duo too. And there's even a H3 called tritium. So people just like their names. Okay, so let's talk about some of these. Let's start off with this top left one. Divide down the middle, and let's start on the left side. Can I get a thumbs up if you think the top one won, and a thumbs down if you think the bottom one won?
For what side?
For this left side here. Thumbs up. Most everyone's saying the top one wins. Great. Easy one where we get to the substituents here, and we have carbon, carbon, hydrogen versus carbon, hydrogen, hydrogen. Great. The right side, also easy. Thumbs up or thumbs down, who wins, top or bottom? Top, just atomic number. They are on Z-same side, so this is a Z alkene. Great. This top right example, right side here, who wins, top or bottom? Bottom, great. And it's because the atomic number, carbon, highs, so we are comparing HHHDDD, isotope wins, great. Now, left side, a little bit harder. Who wins, top or bottom? Thumbs. Bottom. Let's trace it out. Let's see. So we have a carbon versus carbon, they're tied. We look at substituents, right? So this carbon substituents, 2 carbons and a hydrogen. This carbon substituents, we count a double bond twice. Carbon, carbon, and a hydrogen. So they are tied. We move one out. Now, on the top one up here, we have a branch. Does it matter which side of the branch we do? No, they're exactly the same. What if it was like this? Did it matter, or would it matter what branch we chose? Yes. And so what do you do when you're in this situation where you have 2 branches that are different? What do you think you should do? Go to the higher priority one. So the one that seems more complicated or bigger, go down that one, because again, the goal is to win the game of the priority ranking. So that is how the system works. But let's just, for this one, go to this carbon, and we are hydrogen, 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 okay? So then we're comparing it to this carbon, and what are its substituents? So our double bond, this is the weird part, we both count it twice when we go out this way, like when we were doing the blue one, we count it twice here. But also on the green one, we count it twice, or we count it on the green one, I should say. So like it is counted both for the forward and the reverse. So we would say the substituents on this are C, H, and H, because we have our 2 H's here, and then we use the double bond. It feels a little bit weird because it feels like we are going backwards, but here it is. So with that, the bottom one wins. Y'all were right. Then they are both on Z-same side, so it's overall a Z alkane. What about this alkene right here? Is it E or Z? E, Z. Did I ask a bad question? Yeah. So actually, how you would label this, if we asked you to label, is like, what is this alkene? You would say neither. And it's neither because when you divide it in half, it's exactly tied on one side. And if it's exactly tied, you just can't do anything. So maybe that might inform your answer for this bottom one. So on the bottom one, on the right side here, top or bottom, which one wins? The bottom. I believe so, yeah, because this is CNH and this is NHH for these 2 carbons. And then, who'd you get as the winner on this left side, the top or the bottom? Neither. It's exactly tied. This is the same. This is the same. This is the same. I did a dash versus a wedge. You don't need to worry about that. Like I could have just done these on a line and that would be fine. Because that does not change the priority ranking rule. So overall, we would say this is neither. So with this, not incredibly hard, right? Like there are a few like tricks that we need to know in terms of like how to deal with double bonds, things like that. But this should be the points in the exam that, like Logan said, are kind of low-hanging fruit of like, you just do the algorithm and you get through. So these ranking rules that we just did for E and Z, the hardest part was actually doing the ranking here. Whereas when we go into R and S, the ranking becomes the easy part, and then we have to think about this 3D component. So let's move on and talk about this R and S assignment. So just like with alkenes, we want terminology to like describe specifically an alkene as like E or Z. For stereocenters, we want to be able to describe exactly what that molecule or what that specific stereocenter is. And so We call these labels RNS the absolute configuration. We're telling you exactly who she is, her legal government name. So when we do our RNS naming system, we use the exact same ranking rules as with E and Z, but a key step here is we have to orient the molecule so whatever is our lowest priority group is going away from us. Once our lowest priority group is going away, we trace 1 to 2 to 3, and if it's clockwise, we say it's R. If it's counterclockwise, it's S. So with RNS, there are basically 4 scenarios total that you can run into on exams. The first one is normal mode. So normal mode, we have our lowest priority group going away from us, which is what we want. And so when we go to trace our priority, 1 to 2 to 3, okay, we do our normal thing, clockwise is R. We're done, easy, so fine. Then we have opposite day mode. In this case, our lowest priority group is coming towards us. It's the exact opposite of what we want. So we trace our 1 to 2 to 3, but we know it's opposite day. So it normally, or like right now, it looks like it's going counterclockwise. So normally we'd think counterclockwise is what? S. But opposite day, this is actually going to be R. I think it's helpful. Like, you are going to have a lot of writing on your molecules when you are doing this, because it's not going to be a nice 1, 2, 3. You're going to have already done ranking. You might be doing some of this like notation that we saw over here on your molecule. It can be a little bit messy. So one thing that I think is helpful is once you have traced the 1 to 2 to 3, just separately writing it out somewhere else so that you don't get backwards on the clockwise, counterclockwise, which sounds very basic, but it's so easy to make one mistake on these problems and then you've missed it because there are only 2 answers, like answer choices. And so I like tracing out the direction, and then if it's opposite day, just reminding myself of that here. The hardest way that we can ask this is if the 4th priority group is in the plane. When the 4th priority group is in the plane, we don't have an easy shortcut, and so we need some strategies to deal with it. One very valid strategy is to build a model and look at it. And like you can rotate it in your hands and be like, okay, I'm holding it with the lowest priority group away, then I trace 1 to 2 to 3. But I want you to have some other tools as well. So one tool that we can do is we can redraw our stereo center so that our molecule has our lowest priority group not in the plane. So here is the strategy. If you have your lowest priority group in the plane, identify what other atom is in the plane. And what you are going to do is you are going to imagine that you are holding on to the molecule by that atom. So this is kind of my rudimentary version of like a hand or a claw that's keeping this fixed. And then what we are going to do is we are going to imagine that we are spinning around, and I'll do this in kind of this color. We're going to try to spin around this bond. So we are going to take 4 and spin it around and put it in the position where 3 was. 3 is going to come forward and be where 2 was, and 2 is going to go back to where 4 was. Can you kind of imagine that twisting motion here in the plane that we're doing? It's something where I actually think that the drawing out some supports here is going to be something that helps you, whereas if you try to do it in your head, it's easier to make mistakes. So when we rewrite this, what we are going to do is we are going to keep our number 1 priority at the top, because that's where we were holding it from. It did not change. We said 4 moved over here onto the dash, 3 moved forward to the wedge, and 2 moved into the plane. And now what we have done by doing that is we haven't made a new molecule, we have redrawn the same molecule with a rotation that is helpful for us. Because now, what mode are we in? Normal mode or opposite day? Normal mode. So what we can do here is just trace our 1 to 2 to 3, and it's clockwise, so it's R. So I'm going to do one more example here with this last version. So the strategy is we hold it by whatever the other thing is in the plane, whatever's not the 4th priority group. We're going to hold it over here, and then we are going to rotate around the bond associated to that. So we are going to rotate this one 4 back down to the dash, 3 up to the wedge, and 1 in the plane up here. Redrawing that, we keep 2 exactly where it was, 4 we said went to the dash, then 3 goes to the wedge, and 1 goes up top. So then we are in normal mode, trace 1 to 2 to 3. It's clockwise is R. So, like all of these were R, literally these are 4 different ways of writing the exact same stereo center. And like I did that on purpose to be like, part of the challenge here is to, I don't know, acclimatize yourself to seeing the same thing in different orientations. One thing that you've seen in this lecture is you can draw one molecule many different ways. And you're needing to build up some proficiency with kind of interconverting between all of those. Now, there's one more method I want to show you. The in the plane I like because I feel like in the plane with this like rotation, it takes a minute, but it requires very little visual skills. Like you're able to kind of mostly use like little guides with drawing to get everything to where it needs to go. And again, it's not convenient, but I think you don't have to do a lot of 3D visualization in your head, which different people have different comfort levels on. So this is my preferred way. But there is also a hand method, a thumb method. So what you do in the thumb method is you put your thumb in the direction of the lowest priority group, and then with your fingers, you trace the priority 1 to 2 to 3. So here, I'm doing it with my left hand, and if I try to do 1 to 2 to 3, 1 is up, but then 2 is forward. So do you see how I'd have to break my hand if I trace that with my left hand? But if I do it with my right hand, thumb here, and I trace 1, 2 forward, and then 3 back, do you see how my hand can curve? My thumb is in the right direction, 1 is up, 2 forward, and then back, and I'm able to actually follow that priority. Since I did it with my right hand, it's R. If I could do that closing of the hand with my left hand, like I'll draw the other version of this. If we had 1, 4, 2, 3, so this should be S. Then with my left hand, I am going to put my thumb in the plane of the lowest priority group, fingers up at the highest priority 1, and then I close down. So 2 is going away from me, and then 3 is towards me, and my hand curls in the direction of that priority. It's my left hand, so it's S. If that was like, I am not following, that is more confusing, then do not worry about it. I'm kind of showing it to you because there are so many different strategies that you can use to do this like 3D element. And you can certainly try it out in the practice that we're about to do. No matter what option that you choose, you're going to have to practice it in order to get like efficient and proficient about it. Are there any quick questions about that hand method? Yes?
How come the opposite day is like R and then like what you just drew is S? Like why would it operate the opposite like not doing S?
So what I'm saying here is opposite day is opposite what we want when we are assigning our rules. What we want is the 4th priority group going away from us. But here it's just drawn as the 4th group coming towards us. And again, that like the 4th group coming towards us or away from us, it doesn't necessarily mean that it's a different molecule, a different structure. And so here, if we followed our rules as if it was like a normal mode and we ignored the fact that this is not what we want, 1 to 2 to 3, this looks S, and then we use opposite day. But this is still just another way of drawing this exact same R stereo center. Yeah. Yeah, I'm back there. Yeah, you could rotate it into opposite day, but if you have a choice, why not just do normal mode? Because then it has one fewer step.
Are you saying opposite day to normal?
Oh, yeah, you can do opposite day to normal mode too. It's literally whatever is fastest, and typically opposite day is one of the fastest things that you can do. But with that, I'm going to let you guys start working on a practice here, and then I'll circulate. But try out these. So these are also ones that I made. First thing that you're going to do is you're going to be ranking the priority of the 4 substituents, and then you're going to try either normal mode, opposite day, or rotating in the plane. And I'll leave this up so you have some of the work here too. Yeah. Yeah. So it's first I'm going to do it with my right hand. My thumb goes in the direction of 4. Do you see how it's like parallel here?
Why are you turning the hand though?
Because I'm having to put my thumb in that, or like, I guess you can do this way too.
Yeah.
Thumb is 4, fingers up at 1, and curl 2 to 3.
Okay. Yeah. And then the other one.
If I tried to do this with my left hand, I would have to break my hand. Like there is no way. And like here, if I put it this way, I can't curl on. Like there is one hand where it will work for, and one hand where it will not.
Oh, because and for the second one, for example, it would be one. Sorry, we will take each to be.
Mm-hmm. And then your fingers start out towards you because one is out, and then you curl 2, 3.
And if I were to do it with my left hand, it would be. Oh wait, yeah.
Yeah, it doesn't work. It doesn't work.
Okay.
I left my little model kit in chemistry office on a run. Get it?
This is the one I pushed.
The same. Yes. Or the company.
In the flight. That's what I was trying to do.
I might have to do it later, just because. Sorry.
That's okay. Don't worry.
Okay. So let's talk about these. First things first, check your ranking. Because if your ranking is wrong, then you can't do the SRR step correctly. So take 1 second and just rank the priority or check your rankings. It sometimes feels a little weird when we have ethyl and methyl, but remember what those stand for of either CH2, CH3, or just CH3 here. So with that, let's start with this top left one. Are we in normal mode or opposite day or in the plane? Opposite day. So we do our tracing 1 to 2 to 3. It is clockwise, but it's opposite day. You see how, like just then, I said clockwise, I almost said R. But remembering that's opposite day, I think doing something to write down that is opposite day can help save you. So if it's clockwise, but it's opposite day, it's actually what? S here. Because normally clockwise would be R, but we said it's opposite day. Then let's try this bottom example down here. So are we in normal mode, opposite day, or in the plane? Well, our lowest priority group is just the methyl, right? Because all of them are carbons, and this one's the smallest. You can do the tracing out and like do the whole tiebreakers and everything. So we have our fourth priority group going away from us. What mode is that? Normal mode. That's exactly what we want. So we trace 1 to 2 to 3. It's clockwise, so it's R. Those will be the easiest points on the exam, normal mode or opposite day. And then we have the in the plane. So I'm going to try it a couple of ways to just show you working through it. So first, I'll do the draw it out way. I hold it by the other atom in the plane. Then I'm going to rotate around the other 3. So when I redraw it, I need to make sure my bonds are in the same spots. And my first priority stays at the top. My OH stays at the top. Fourth priority, I rotate it around to the dash. 2 came up front, and then 3 is now in the plane. So now we're in normal mode. We trace 1 to 2 to 3. It's counterclockwise, so it's S. Another way that we could do it is we build a model. So one thing that, or I'm going to tell you a few structures that if I were in your shoes, I would build them and just have them going into the exam with me. One is just a stereo center, one with 4 different colors on this, so that you can apply it to any stereo center that you see, and suddenly these colors can represent what's going on. So here, red is up top, the OH, blue I'm doing as the hydrogen, green is the methyl, and then orange is the ethyl. So if I wanted to use this to help solve R and S, all I have to do is hold it by the lowest priority group, which is the hydrogen, and hold it away from me. And now, with this, I trace 1 to 2 to 3. 1 is red, 2 is green, 1 is red, 2 is orange, 3 is green. 1 to 2 to 3. Is that clockwise or counterclockwise? It's counterclockwise. It's S. So, again, I think this is also a really simple, easy tool to use. We can, yet again, do our little hand roll. Our fourth priority is here in the plane. We put our thumb with that. We flatten our hand to line it up with our first priority, and then we curl our hand and see if it matches 2 and 3. 1, 2 going away from us, 3 going forward. It works, and this is on my left hand, so it's S. So there are so many different tools that you can use. You don't need to be proficient at all of them. You need to be proficient at one. So whichever one feels like it's going to be a good vibe, good fit for you, pick that, go with God. Cool, yeah.
For the model, can you just, when you were showing the model for that
Mhm.
one, so OH and H are both in the plane, right?
Yep, so they're both in the plane. This is coming towards you, the methyl, and this going away. And then, in order to get it to where you can solve it, you just hold the fourth priority group away from you. And then you trace 1 to 2 to 3 with your colors.
Thank you.
Yeah, totally. And with that, you can't use colors on the exam. You can't use colored markers. You only use pencil. Please do not use pens on the exam unless you're about to score a 98% on that exam. Then you can use a pen. If you're that girl, sure. Otherwise, use a pencil. No. Yeah, seriously. But you can do R for red, but then R and S, it's confusing. Get some sort of shorthand system of this thing is red, this thing is green, this thing is orange. Do whatever you need to do. But with that, I need to keep on chugging to get through everything, okay? So let's back up a little bit and talk about chirality. So this is also one of the lectures that had the most definitions to it. So there's a lot of terms. And one kind of heads up I want to give you is the definitions for these terms varies a lot between organic chemistry classes. So what one class calls a stereocenter, another class might have a slightly different definition that could include more things or fewer things. So these are our definitions for this class, but just be warned if you're looking at other resources, it might not be exactly the same. So first off, we have a stereocenter. A stereocenter is a tetrahedral atom, typically carbon, what we care about, bonded to 4 different groups. Looks like her. Then a chiral molecule. Chiral is a descriptor for a whole molecule, where a stereocenter is talking about one atom. A chiral molecule is a molecule with a non-superimposable mirror image, which when I say non-superimposable mirror image, like, it just like, what does that kind of mean? So what it means is we can generate a mirror image. We can imagine that there is a mirror right here. This molecule is looking into the mirror and generate this mirror image. And when we generate a mirror image, do not always know if we have generated the same molecule or a different molecule. It depends on if the molecule is chiral. But for a chiral molecule, and typically here, our main criterion for whether or not a molecule is chiral is whether or not it has a stereocenter. So we have a stereocenter, so the molecule we do think is chiral, correct? So when we generate this mirror image, we believe that we are generating a new molecule that is different from the one that we started with. But what we can do is we can start to rotate this. We can move it around, and we can do a pancake flip. A pancake flip is literally turning something upside down, and we can rotate it around. And here, this pancake flip is just another way of redrawing this same molecule from the mirror image that we generated. And then we can try to literally drag this on top of the original one. That is trying to superimpose them. And if we do that, what we see is these two overlap just fine, but the hydrogens and fluorines here don't add up. Like, they don't match. And so we would say it's non-superimposable. And mostly these are going to be reference guides for you to go back and look at. And a lot of this is like, how much do you need to convince yourself of this, to see it, and to kind of understand it? It takes some working. Oftentimes it takes building it out and just like seeing it and working with your hands. But however, if we start off with a molecule without a chiral center, like this one, I have drawn it out with wedges and dashes, but is this attached to 4 different things? No. So when we generate our mirror image, we're actually generating the same molecule again. And if we do our kind of rotation and try to lay it on top again, we see we can get it to exactly line up. In this case, we say it's superimposable with its mirror image. And so that is achiral. All of this, chirality, is a proxy for talking about symmetry in molecules. If we have a stereocenter, we have a source of asymmetry. We have something that's going to throw off symmetry. Whereas if we say a molecule is achiral, it means that it has some degree of symmetry to it. So we need a really quick, easy check for is something chiral or not. So if there are 0 stereocenters, we say it's achiral. I know Logan gave like an example in class of like a really rare case. We will never ask you that. For our class, 0 stereocenters, achiral. 1 stereocenter, it's definitely chiral. Easy. 2 or more, we have to do a little check. We have to do a little work. So remember, we use chirality to talk about symmetry or asymmetry. We say if there's asymmetry, there's no symmetry in a molecule, it's chiral. But when you have 2 or more stereocenters, what you could have is an internal plane of symmetry within the molecule. And if you have that internal plane of symmetry within the molecule, that is symmetry, right? And so if it is symmetry, then we say that this molecule is achiral. It's really frustrating because asymmetric is chiral, and then symmetric is achiral, so the A's don't match up, and it can be a little confusing at first. But essentially, when we have 2 or more, we have to do this check for what's called mesocompounds, compounds that have this internal plane of symmetry. So let me show you kind of like on a model kit what this looks like. So here, can you verify that this is a stereocenter? It's connected to 1, 2, 3, 4 different things. This top one's a stereocenter. This bottom one, it is also a stereocenter, right? Connected to 4 different things. And if I rotate this, I can see, cutting it down the middle, there's an exact plane of symmetry where this whole side matches this whole side. So there's symmetry present. We call it achiral. It's a mesocompound. But then, if we look at a similar setup over here, can you verify that this is a stereocenter up top? This one's a stereocenter too. And then we try to line it up. 1 second. We try to line it up, And when we line up the red ones up here top, we see that the blue is forward on one, blue is back on the other. Would this be an internal line of symmetry within the molecule? No. So it doesn't have the symmetry, so it's chiral. The hard part is, when we draw the molecule exactly like this, you can check for the meso check. And I often say that, like, it's the last thing that you have to check. You have to ask, hey, what about me, Zoe? Don't forget me, Zoe. And because oftentimes you'll just forget. Like, you want to do chiral, achiral, and be done, and 0 and 1 are really quick. When you are doing this check, it's often going to be tricky because we will give you molecules written out like this. The way I've written it, we can't immediately tell if there's an internal plane of symmetry or not, right? We can verify that there are 2 chiral centers, but we have to do our meso check. So what I recommend doing is I recommend building a 2 stereocenter unit like this and bringing it with you to the exam. And this is going to be your meso checker. So what you do is you assign colors to your molecules. So I'm going to make my chlorines red. I'm going to make the hydrogens blue. And if you have a model kit, could you try to build one of these with 2 carbon center? Take a minute with me. That sigh was real. And then I'm going to call the methyls green. And what it should look like is just 2 stereocenters glued together, ideally each with the same colors on it. So like each one having a blue, each one having a green, each one having an orange. Something like this. So once I've built this here, the big thing that when you are building it, you have to make sure that you actually did a good job of building the molecule that's on the page. It takes a little practice. So we have the red chlorine up and in the plane of the page. Then we have this chlorine down and forward, coming out at you. Then we have this methyl up and in the plane. So this is the plane, anything in front of it's coming towards you. And then we have this one coming towards you on a wedge. Finally, the hydrogens, this one's away from us, so it's on the dash. And then here, this hydrogen is also away from us. So we've done our check. We verified we have built the correct molecule here. If you built it another way, you might just have to unplug and replug in like 2 atoms, and then you'll get it the right way. So once I have this model kit, then I don't need to look at the paper at all anymore. All I need to do is I need to twist this to line up 2 of the colors. And here, do we have an internal plane of symmetry? No. So we hold the reds together. We see that green's forward on one, blue is forward on one, blue is back on another. And so this is not an internal plane of symmetry. So it's not meso. So we would say that this is just straight up chiral. The other thing that you can do is you can try your rotation trick. You can try saying, okay, I'm going to make my chlorine in the page here. I'm going to send my methyl back and my hydrogen forward. And when I redraw it, the right side of the molecule is staying completely the same. So this part is exactly the same. But after the rotation, I moved my chlorine up here. Then I moved my methyl into the dash position. And then I moved my hydrogen to the wedge position. And here we can verify that this is not a plane of symmetry. So use, again, whatever tool feels most natural to you, but that is the process. You have to do, if we give you something where it's not readily apparent, if there's an internal line of symmetry, you have to either build it or redraw and rotate it in order to verify whether symmetry is there or not. So with that, let's go to practice 3, which I put some of the practice at the end just to save space and to help with some of the layout things. So practice 3, these are questions on page 18 of the problem set. So these are A through D and then J. All of these, you're going to ask yourself first how many chiral centers it has. If it's 0, it's achiral. If it's 1, it's chiral. And then if there are 2 or more, we have to do our meso check. So, would you prefer to see these up here, or would you prefer to see like the tree and like the meso page? Meso page? Okay. And just know that this is page 18 that we're working on.
Why is that not a meso?
Because the hydrogen's going forward on one and back on the other.
This is my bad.
So, oh, you,
I rotated it that way. Oh, am I not allowed to?
but here,
Oh, wait. And then.
yeah, you rotate that side and that side needs to stay the same.
And then.
Yeah. So if you want to start off with the easier one and then go, actually, no,
Yeah, that's great.
so that, this is, like, all of this is something weird. They play a symmetry is, so do you see how, do you see how along this part goes down, like the big part of change, and this part goes up? We can't compare the symmetry. No, it's all good. So what we need to do is we need to get into here, we rotate this molecule somehow, or we build it, and we compare it so it's like this, or like the rest of the chain can look like this, like that. Because then we're putting it in the same case on both sides, and we're seeing how the wedges and axes all work. But until we do that, we can't figure that out. So yeah, you can. That's a valid strike number, definitely. For this, again, I'm like very curious as to check this together. And to me, it's a lot easier to do an actual building. Let's see that. So like imagine the red is the person in plane, and then here the green is the bromine. So bromine's going up over here, it's going down over here, but they're both out towards you. If I rotate this, then it's really apparent that there's no internal symmetry here. Or you try drawing it out from both places. It's whatever strength, as long as you're getting the right message. So, like, okay, if you flip the rotation, so here, like, let's say the red is the chain that's in the plane. So the plane is here. You see how it's going up in the plane over here, down in the plane over here. Let's say the greens are bromines. So do you agree these are going out towards you? And then we go to the right. So we built this model. Okay, well now I'm gonna rotate it so the greens are both up top. Because we're trying to compare. Like, all we did to do that is to confirm that we built the right molecule. But in order to see whether it's meso or not, what we have to do is we have to confirm that there's going to be a symmetry. But whether it's wrong, I can't tell. So I'm going to do it so that green and green are here. Because if there is symmetry, it would be here, right? And here on either side. But when I remove this, you see how on this side it's blue, this side is red. So that is not a plane of symmetry for the molecule. Yeah, it's not going to work out. Whereas, if it is meso, it'll exactly line up. Yes. I mean, that would be crazy.
I'm gonna get a big ass mirror.
So that, and then I would make probably something like this, where it's like two stereocenters that are connected to each other, each with the same color. And this is really good for doing this meso check. Okay, so for these, let's talk about it. I'm gonna go and do the easiest ones first, just because we can get them out of the way. So, how many stereocenters does this molecule have? None. So is it chiral or achiral? Achiral. Cool. That's the only easy one. Let's try this one. How many stereocenters does it have? 2. It has 1, 2. Okay. If there were potentially a plane of symmetry, it's going to be through the oxygen, right? And we need the mirrors to match on either side. But do our wedges and dash line up on either side of this potential mirror plane? No. So we don't have an internal plane of symmetry, and we have 2 stereocenters. We're just chiral. I would say, like, not a mirror plane. Okay, let's try this bottom one down here. This is a little tricky. How many stereocenters do we have? Can you show me on fingers? 1, 2, 3, 4. Work. I see most of the right answers. So 2. So we have stereocenter here and here. And it is, this top one's not a stereocenter because 2 chlorines. So these 2 are the same. Okay, and then if we had an internal plane of symmetry, it would go divide like this, right? And we see that here both these bromines are up on wedges, so that's a promising sign. But the way that we draw this here, this doesn't look like it's on the mirror plane, right? But it actually is on that mirror plane. And I think I have a little thing where I made this somewhere, if I can find her. Yeah, so I made something like this. So, here is the one with the chlorines, 2 chlorines on it. Here, the purple are the bromines. So do you see how actually, when I look at it this way, and I make my mirror plane right here, both of these green atoms are actually on the line of the mirror plane. And it's because when we do a dash and wedge, even though, like, when we write it, one looks like it's going a little bit to the right, one looks like a little bit it's going to the left, these are really going up and down. So this is on all the same mirror plane the whole time. And so we do have an internal plane of symmetry. So we would say we are meso, which is achiral. So those were the, quote, easy ones, or slightly easier ones. Let's try these harder ones up here. So this one, we have 2 stereocenters present. What I would do is I would try to build this. So what I'm doing is I'm going to make red the parts of the molecule that are in the plane here. So I'm going to make it like this, all in the plane. Red is kind of up in the plane and down in the plane over here. And I see green is going to be my bromine. They're both coming towards us, but one is up towards us, one's down towards us. And then the fluorines are away from us. So can you confirm we have built this molecule correctly? Is that okay for most people? Once we confirm that we built it correctly, we no longer have to look at that, and we can just work with our model. I'm going to put 2 colors up at the top, and then try to divide between them. Is there an internal plane of symmetry? No. So this is not meso. This is straight up just chiral. Then the last one over here. This one is a little bit tricky to see as well. So we have 1, 2, 3, 4 stereocenters. If we had an internal plane of symmetry, it's going to be somewhere in this land, right? It's going to be kind of between these 2 parts of the molecule. But this long chain portion is in the plane going down over here, and it's in the plane going up over here. If we want to be able to compare it to see if there's a plane of symmetry, we either need to rotate or redraw it so that it's down on both of them. So it would be keeping this part all the same, and then we are rotating the other side to be like this. And then, based on where our wedges and dashes are, we can compare them. On the annotated notes, will have it rewritten out as like what if we did a rotation on paper, but but I think it's going to be easier to just look at the molecule set and try to figure it out. So I'm going to make orange in the plane over here. So orange is over here. Then I'm going to make my methyls blue. So this methyl is blue, it's going towards you on this one, and it's going away from you on this one. And then the other ones that are not written in there are, we have a hydrogen. So a hydrogen going away there and going forward there. And I guess our hydrogens are going to be green. So going away on this one, forward on this one. Do we feel okay that this represents accurately the molecule that's on the screen? Sure-ish. And again, it'll take some practice to do that verification. Then we can just work in the model. I rotate. Is there an internal plane of symmetry? It matches exactly on either side. So this is our special case. It's meso. And then it would be achiral overall. This will take some practice. It's not intuitive. So again, my favorite tool is doing the two stereocenter models and building them that way. There's also rotations. There are also many other ways. Some people can just see it. If you're a person that can just see it and you get it right, go and enjoy life. Couldn't be me. With that, I'm going to keep on chugging to more of our skills. So we have isomers. We have a bunch of definitions here, and we have like a little tree to help us figure out our types of isomers. So if we have same molecular formula, different arrangement, that means that we are broadly in the isomer camp. And then we ask, okay, do our molecules have the same connectivity? Like, is every partner bonding to the same people? Like here, we have C5H12, and we have 5 carbons. Here, they're all in a straight line. This is our normal pentane. But here, we could group our 5 carbons differently, and we would say we have a different connectivity. Because here, 4 was connected to 5. Here, 3 is connected to 5. So these are constitutional or structural isomers. Easy enough, you've seen those before. Everything else falls into the stereoisomer camp. So isomers that have the same connectivity, but a different 3D structure. Once we're in stereoisomers, we have 2 camps. The first one is enantiomers. So these are stereoisomers that are non-superimposable mirror images. And hey, we've heard that phrase before in our definition of chiral, molecules without a superimposable mirror image. So, like a lot of times, if you are a chiral molecule, you have an enantiomer, and you can generate it a few different ways. There are 2 main ways that we can generate an enantiomer for a molecule. The first one is an outside mirror plane. And note that this is different than the mirror planes we were talking about in meso, because those were inside of the molecule. This is outside the molecule. When you are doing an outside mirror plane, you mimic everything on either side of the mirror. So we have our structure here. And then here we see the nitrogen is closest to the mirror, so it needs to be closest to the mirror over here. And everything stays the same in terms of wedges and dashes when we do a mirror. Then over here, both are on wedges. But if you actually did do RNS assignment, both of these would be R, and both of these would be S. So we know that this is a different molecule. So there are 2 definitions that can help you determine if things are enantiomers. The first one is it's a non-superimposable mirror image. So you can do the mirror image thing, but oftentimes you're having to do a lot of drawing for mirror images. So we need a simpler version to check if something is an enantiomer. And the simpler version is if you write the molecule with the exact same carbons in the same spot. So I'm going to put like a star over here and a square over here. And then you just swap all the wedges and dashes. So I make this dash OH, and then I make this a wedge NH2. If you did the RNS, this would be both S again. And so it is also our enantiomer. So this is a thing that's going to be really cringy and embarrassing, and you can laugh at me, because I really was trying to do Pavlovian conditioning again, and I couldn't make it work well. And so I made a little thing. It's really cringy. I can't believe I'm going to do this. Enantiomers. Non-superimposable mirror image. Enantiomers. 1. All swap. Now, I am going to make you do it with me. So I'm going to do it one more time for you to listen. I tried to like, the emphasized beats are in red, and then we have the claps, and we're going to go straight in order. But I'll do it one more time. Enantiomers. Non-superimposable mirror image enantiomers. All swap. Can we try it together? 1, 2, ready, go. Enantiomers. Non-superimposable mirror image enantiomers. All swap. Hey, look at us. Okay. That actually wasn't as horrible as I expected. I do believe that I'm a little bit red now because it feels very embarrassing. Thank you. So we have our 2 checks for if something is an enantiomer. But if we are stereoisomers and we are not enantiomers, then we are diastereomers. I literally call it the junk drawer. It's where we put all of the other stereoisomers. So it could be the case where, look, we have the star carbon in the same spot, we have the square carbon in the same spot, and we've swapped one of them, but not every stereocenter. So if we swap some but not all, are we an enantiomer? No, enantiomers all swap. So if we swap some but not all, we're in the junk drawer. We're diastereomers. Another thing that goes in the junk drawer are E and Z alkanes, because are these 2 things mirror images of each other? But are they the exact same molecule? No, the E and Z are different molecules, so they're still stereoisomers somehow, but they're not enantiomers. Put it in the junk drawer. They're diastereomers. So these are kind of our terms and definitions. And I'm going to do 2 more terms and definitions before we get into some more skills and practice. So conformation and configuration. So conformation is just kind of how the molecule is sitting. It's the arrangement of the atoms in 3D space that can readily interconvert by just rotations around single bonds. So like over here, looking at these 2 examples, I can go from this one to this one just by doing a rotation, moving the hydrogen down here, the methyl up here, and the chlorine back. I'm rotating around this single bond right here, and I can draw the same molecule a different way. So we say that these are 2 different conformations of the molecule. Newman projections are exactly the same thing, rotations around single bonds. So I'm going to keep this top one the same, and on the back carbon, I'm going to rotate the nitrogen over here, the methyl over here, and the hydrogen over here. And this is the same molecule. I just did a rotation. So we say these 2 are conformers of each other. Same thing with chairs and doing those ring flips where they wiggle, which we'll talk about a little bit later. So conformations can be more or less stable, but it's still the same molecule. This is still our dog Spike, and this is stable Spike, this is unstable Spike. Different conformations. Configuration is who she is. It's her identity, R or S. If we build something and it's R, and we rotate it, it is still R, no matter how we draw it. And so it has to do fundamentally with like what is this molecule's actual identity. And here, there is no way where we can get from our R stereocenter to our S stereocenter without physically undoing bonds and replugging it in. I invite you to convince yourself of that fact with molecules if you don't already buy it. So, this is one configuration, that's our dog Spike. This is an alien named, I don't know, Leela, who is trying to infiltrate our society and learn our government secrets. That's who she is. These are different configurations. So R and S is configurations, E and Z are configurations, conformations how it's sitting. I know that was a lot of like vocab soup. Let's keep on plowing, and let's talk about the biggest skill. The hardest thing from this lecture is this skill called discerning stereoisomers. So what we are going to do, and you saw it a little bit in lecture, is we are going to give you 2 molecules, and we are going to ask you, how are these molecules related to each other? Are they the same molecule drawn different ways? Are they enantiomers? Are they diastereomers? Are they constitutional isomers? And so we need a running list of questions to ask in order to diagnose what's going on here. So let's start off with, do these molecules have the same molecular formula? Do they have the same atoms in the same quantity? You could count like all the C's and H's, but I'm gonna let you vibe check on it. Do they look like they have the same molecular formula? Yeah. Do these molecules have the same connectivity? No. Because over here you have a carbon that's connected to a hydrogen, methyl, and nitrogen. And over here, the carbon that's connected to the methyl is connected to a carbon, carbon, methyl, and hydrogen. Like there's no nitrogen. I guess I can also say this one's connected to a carbon over here. So different connectivity, but same molecular formula. What are these? Constitutional isomers. So that's kind of the first check that you want to do on two molecules. Are they connected the same? Okay. Second question. Are these the same molecule? So when we are looking at these molecules, they look pretty darn similar, right? They have the same connectivity. And one tool that is really helpful, but is often misused when students first learn about it, is pancake flips. So pancake flips and rotations provide us with different ways of drawing or looking at the exact same molecule. So let me try out an example here. I tried to do an infographic that later on you can go back and look at and trace all the atoms on your own. But a pancake flip is literally taking a molecule and turning it upside down. You've already seen that. But what does that look like if we actually try to draw it out? So here, let me do it this way. Here I tried to draw this square for you. The purple is the bromine. Do you see how it's coming out? And the ethyl is back here and is going away. And then our methyl is coming out. Can you verify that this is the correct molecule on the screen? That's always the first step. So now let's say that we wanted to try to do a pancake flip of kind of like over this line, like turning it over blanc. Then let's see what happens. So the carbon over here that had our ethyl, it was the leftmost carbon, but when we flip it over here, it's now the rightmost carbon, right? So when we flip it over, our ethyl is now over here, blanc. And is it coming towards you or going away from you? Towards you. So now it's on a wedge. Okay, let's do the same thing for the bromine. The bromine was right here, it's coming towards you. And then if we pancake flip it, now it's in the top left and it's going away from you. So we're going to put our bromine on a dash. Then, finally, this bottom one, let's pay attention to it. So it's towards you, but when we pancake flip it, now it's away from you. And also, just to double check, over here it was right. So then when we flip it pancake, it's going to be on the left now. So, like generalizing this in a few different rules, when we pancake flip, we didn't make a new molecule. But when we turn it over, all the wedges turn into dashes. And they flip the side of the molecule. And it's important that both of those happen. If you only did one of them, like if you only did swapping out the wedges and dashes, and you kept everything on the same side, then what did we generate? All swap, we generated the enantiomer. And so it's the combination of swapping all the wedges and dashes and flipping it over to another side of the molecule. Like the carbons can't be in the same place after you've done a pancake flip. So try to do a pancake flip of this molecule. And again, with the pancake flip, we are just trying to redraw the exact same molecule in a different way now. So when we do our pancake flip, for the backbone, the rightmost one now becomes the leftmost one. So then the one connected to it's going to have the OH, and now is the OH on a wedge or a dash when we pancake flip? A wedge. Okay, then we go one over and we have chlorine, and now it was on a wedge, so now it is dash. So again, these are the same molecule. It's not our mirror image generating an enantiomer. So this just gives us another vantage point to check things. So if we go up here, let's try to do a pancake flip of this molecule. So the way that we have it, the methyls or the purples coming out at you, And then the ethyl is going to be this green going away from you. And then if we flip it over, then it's going to look like, well, now these are both going away from you, and the ethyl is coming towards you. And if I drag this over, that's what we have over here, right? So, are these the same molecule? Yeah, we did a pancake flip to go from one to the other, and pancake flips do not change the identity of the molecule. It's a tool for rewriting the same molecule a different way. So are they the same molecule? Yes. It's going to take some practice. Bear with it. Then, after that, we check, are these enantiomers? So there are lots of ways that you can check for if two things are enantiomers. If they are all in the same positions, you could check if they all swapped. So these look pretty similar, but what if I just take this and I'm going to redraw this right one, and I'm going to just rotate it this way. And I'm going to make it so that this carbon is moved up top and this carbon is moved right here. Do you see how that's just a rotation in the plane of the page? Like I'm just kind of rotating the molecule around. So I've redrawn this molecule exactly the same. And now that's going to let us compare this better with the other molecule. So now when we look at these two, do we see, like we have carbons in the same spots? Do all of our wedges and dashes swap? Yeah. So are they enantiomers? Yeah. That's an easy way to check. So here, I said yes to all swap. Another thing that you could do is you could generate a mirror image and rotate it and see if the mirror image you generate from one of them matches the other molecule, in which case they would be enantiomers. So let's practice the skills of doing that. So if we are drawing our mirror image, it's going to look really similar to our pancake flip, but what we do is we keep everything close to the line of our mirror the same. So if this green carbon right here is closest to the mirror, on the other side of the mirror, the green one's also closest. If the yellow one is closest to the mirror, then the yellow is also closest on the other side. And when you do a mirror image here, you keep all the wedges and dashes the same. OH, H2N. So when we do that, when we draw a mirror image and it's a chiral molecule, you've generated the enantiomer. The other way that equally generates the enantiomer is you keep every molecule or every atom in the same spot. So your green and your yellow are going to be on the right side over here. And then you swap all the wedges and dashes. This also generates the enantiomer. And if you would believe it, these two are the same molecule written a different way. You could do a pancake flip and a rotation of this molecule and rewrite it like this. These are the same molecule. These are enantiomers. So I also tried to do another infographic here to help convince you of that and to work on those skills so you can trace some atoms with rotations and pancake flips and mirrors, because again, they all look pretty similar. So now we've already done constitutional isomers, identical molecules, enantiomers. What's left are junk drawer. So do they belong in the junk drawer? Here, are these E and Z isomers of each other? Yeah, one of them has the ethyls on the Z-same side, one of them has them on opposite sides. So these belong in the junk drawer, they are diastereomers. What about these? Is this a direct mirror image? No, why is it not a mirror image? Yeah, like it's fine over here, but here one is wedge, one's dash. So we know that this is not a mirror image, it can't be an enantiomer, it's in the junk drawer. I'm going to show you one more way to verify that same fact, which is, what if I do a pancake flip of this? So I'm going to redraw this left molecule with a pancake flip, and when I do the pancake flip, the left and right have swapped, and the wedges and dashes have swapped. So now, instead of comparing the original molecule in this one I'm going to compare this molecule and this one because we know these two are exactly the same. And when I compare these, I see, okay, the carbons are all in the same spots, and some, but not all, have swapped. That's our diastereomer definition again. So there are many ways to verify. Do whatever is fastest. Do whatever is easiest to you. So now, these last two, I'm going to skip for now just because we're a little bit shorter on time, and I want to talk about chairs before we finish. But I will have an annotated one, and this is also like in the skill builders. So it's putting all of these strategies together to practice. So last thing, let's talk about chairs. So meet the chair. And the chair, I feel like it has like Toy Story, the claw energy of like, oh, she's this iconic figure. She's out here just sitting like that. Cool. So when we have our chair, we have axial and equatorial position. So axial go straight up and down, and equatorial go out. Bum, 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 bum. And each carbon in the ring has an axial and an equatorial substituent. Now, one thing that's a little bit tricky and that Logan didn't explicitly mention in lecture, but one thing that we can also think about all of these axial and equatorial positions is we can think about, are they up or are they down? And when we say up and down, we're imagining kind of like a god eye looking from above at the chair. So if it is going towards the eye, it's up. And so even this, it's equatorial, but it's going up towards the eye. Then it's the up position. So this is an up axial. This is an up equatorial. Up axial, up equatorial. And then the ones going away from the eye, so axial down, away is easier to see, and equatorial down is like this. We have up and down, and that language is going to be helpful for us when we try to move from perspective drawings to chair structures. The other big thing I want to flag with this is you have to be really specific with how you draw these and the bond angles. So like, I'm going to give some examples of things that would not get good credit. Like even that chair, like it's a little wonky. For the most part, we try to be generous with the drawing, but just try to make it as specific as you can. So one thing that would blatantly not earn points is, what if I make this carbon axial up, but in the actual chair structure, it's axial down? This would not earn points because we have to memorize that this part of the chair structure is axial down, equatorial up. So when I say memorize these bond angles, it's literally where they are in the chair. Is it an axial up carbon or is it an axial down carbon? So that would not earn points. Another thing that would not earn points is, what if I put a substituent like this? Is it clear whether this is axial or equatorial? No. It's literally in the middle. And students will sometimes do that to try to be like, well, I mean, obviously I meant equatorial. And I'm like, literally, did you? I don't know. The other one is like when they are kind of just like cattywampus, so like blomp, blomp. Like I guess this is more up, this is more down. I guess you mean this is up equatorial. I guess you mean this is down axial. But do you see how it's like not a good representation of the actual 3D geometry? So these are the things that we want to avoid. We want very specific angles. The most important thing that you can do with chair structures is go back and forth between a perspective drawing with dashes and wedges and a chair. So let's think about how to do this. What we are going to do is, if we start off with a chair, anything that is up is going to be a wedge in your perspective drawing. Anything that is down is going to be a dash in your perspective drawing. So what I'm going to do is, first I'm going to start off with this green carbon, and I'm arbitrarily going to pick a carbon on the hexagon, and I'm going to say that's green carbon. It doesn't matter where you place it. Okay, this A, is it up or down?
Up.
So wedge or dash? Wedge. Put it on a wedge. Now, you have to be careful because when you go and do the next one, you are thinking about, okay, relative to this eye, I'm kind of going clockwise around the ring. So like here, this is clockwise the next position, so here this is clockwise the next position. You can also go counterclockwise, just make sure that if you do it that way, you go counterclockwise correctly on the other one. Okay, then we have our blue carbon, and is B up or down? So wedge or dash. Great. Then C, if we continue around, so we skip one and then we have the yellow. C, is it up or down? Wedge or dash? Easy. That's easy mode. Go into perspective drawing. That should be no problem. Now, when we are going from a perspective diagram to a chair, we have choices because not all the chairs on a ring, not all the atoms on a chair are the same. So, like, let me adjust her so we can see a chair. So, like, for example, this carbon right here is up axial, but this carbon right here is up equatorial. So, when I do my first choice of where am I placing my green carbon, I could be placing that green carbon on an up axial position, like the generic bond angles for this green one, or this position are here, or I could place it on an up equatorial position. So since we have two options, let's just do both. Let's draw it out. So I need to make my wedge here into an up position. So I'm going to make it the up axial when I assign it to this carbon. I'm going to put in the hydrogens too, just to help us with our chairs. Generally speaking, you're always going to want to draw both of them here on a carbon. Like, we won't count off if you just do this, but it just helps you keep everything nice and neat if you do both of the substituents. And then when we assign it to this green carbon over here, the up position is equatorial now. A and H. Okay, let's keep going. So the blue one, it is on a wedge, so it also needs to be up. We know from our generic chair drawing that the bond angles for this position look like this. So we put B up on this chair, and it's an up equatorial, and H is down. And then for our other chair, we know that this position is up and down, has these bond angles. And again, that's one of the things that you will just memorize when you are drawing your chairs over and over. So now B is up still, and we can place it like this. Lastly, we do the same thing with C. So this position has these bond angles, whereas on the other one it has these bond angles. And we want C to be down. So in the leftmost chair, the down position is down equatorial. And in the rightmost chair, it is down axial. So we've generated our two different versions, but let's think about why this matters. So remember in lecture we said when we place things axial, they are going to have the potential to bump into other axial things. And so we don't like putting big things axial. So we, generally speaking, want to minimize the number of things that we are putting in an axial position. So in this chair, how many things are axial? Yeah, when I say how many things, how many non-hydrogens? So here, one is axial, and just one. So this one has one axial. Now let's look at this chair. How many non-hydrogen things are axial in this one? Two. We have this up axial, this down axial. So we have two axial. So given that, and imagining our substituents were all the same size, which one's going to be the more stable chair, the left one or the right one? The left. So this is a skill that you are probably going to have on the exam, where we give you something like this, and we ask you to draw the most stable chair conformation of this molecule. Or we'll ask you to draw the least stable. Or we'll ask you to draw both and say which one's more stable, which one's least stable. And literally the skill is try putting it on one carbon, and then put it on one carbon over on another one, and compare them. That is how you generate them. This will probably be 7 or 8 points on the test. So it shouldn't be a super crazy thing. You can also generate these two versions by doing the chair flips. I think it's easier to make mistakes when you do chair flips. So I prefer just generating it two different ways. Cool. Any questions on going from perspective to chair? Yeah, perfect.
So if A and B were coming out this way, so why is A axial on the left and B is?
Because the wedge, it doesn't matter axial or equatorial, it matters up or down. So here, it is up, and this carbon is just an up axial carbon. Here, it is still up. It's going towards this eye. Like the eye is up here. Of the two positions, it is going towards the eye. Is that, when I say towards the eye, broad strokes, it's going up or down angled. This one's definitely going down, right? So this one is going up relatively. It's going up at an angle, but it's still going towards the eye.
So all you did was kind of change the way it was.
Yeah, I changed where I signed this up. It was either up axial or up equatorial. Yeah, those are two options. Yeah. So it's a little bit more complicated that because here I drew the same exact chair, whereas when you do a chair flip, you need to draw the other chair, the one that goes blom, 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 blom. And so it's a little bit more complicated, and because it's more complicated, I was just like, I'm going to teach you the easiest way. I'm going to do one last thing, and then I'll do some questions after. So ring flips, I did an example here where I just traced the carbons where they all wound up. And again, see how it's the chair that goes this way on one of them, and it's the chair that goes this way on the other one? That's what makes it a little bit harder. The other thing is if you have a huge bulky group, like a tert-butyl group, the tert-butyl group is so big that she fully cannot be axial. She locks the ring into an equatorial position. So she cannot do chair flips. You cannot draw two conformations, one where she's axial, one where she's equatorial. She will only be equatorial. So given that, let's think about something like this. So here we have both a methyl and we have a tert-butyl on wedges. So they both need to be up in our drawing, right? So can I assign this tert-butyl to this carbon? No. And the reason why is this carbon is an up axial carbon. So if I assign this tert-butyl to this carbon, it's going to put my tert-butyl axial, which is impossible. So I can't assign it to that one. I also cannot assign it to this one or this one because they're all up axial. But remember, it's on a wedge. It still has to stay up. So I'm going to assign it to this up equatorial position, and the hydrogen is down. Then, when I go around the ring, I'm going to skip 1, 2, 1, 2, and then I get this carbon. So 1, 2, I get this carbon. We know that this has to be up, and it has to be on this carbon. So this carbon, the bond angles are like this. So is it going to be up equatorial or axial? Axial, because it has to be up. And so when you have something like tert-butyl, it locks the conformation. You don't have options. So the question that he asked in class today of like, okay, is it axial, equatorial, and the most stable version of this molecule? It was getting at this. We are at time, so I'm going to end section here. This takes some practice. It's a lot of information. It's been a long day. Y'all are doing great. Exam is next Thursday. I will stick around to answer some questions, okay? Have a good weekend. Have a happy 4th. Be safe.
Thanks, Colton.
Yeah.